Another day, another story. The God particle is a nickname for the Higgs boson, a fundamental particle in the field of particle physics. The Higgs boson was proposed as part of the mechanism that gives mass to elementary particles. Here are some key points about it. Welcome to Tabo Eminent Channel. Origin of the term. The term, God particle, was popularized by the 1993 book, The God Particle. If the universe is the answer, what is the question? By physicist Leon Lederman and science writer Dick Teresi. The name was chosen partly to evoke the particle's fundamental importance, though it is often considered a misnomer within the scientific community. Higgs Field and Mechanism. The Higgs boson is associated with the Higgs field, an energy field that permeates the universe. According to the standard model of particle physics, particles acquire mass through their interaction with this field. The Higgs mechanism explains why some particles, like the W and Z bosons, have mass, while others, like photons, do not. Discovery. The Higgs boson was discovered on July 4, 2012, by scientists at the Large Hadron Collider, LHC, at CERN, the European Organization for Nuclear Research. The discovery was a significant milestone in physics, confirming the existence of the last missing elementary particle predicted by the Standard Model. Theoretical foundations. Theoretical background. The concept of the Higgs boson was introduced in the 1960s by physicist Peter Higgs and others, including Robert Brout, Francois Englert, Gerald Guralnick, C.R. Hagen, and Tom Kibble. They were all working independently on the problem of how particles acquire mass. Higgs mechanism. The Higgs mechanism involves the Higgs field, a field that exists throughout the universe. According to this theory, particles gain mass by interacting with the Higgs field. The stronger the interaction, the more massive the particle. The Higgs boson itself is an excitation of this field, much like a ripple in a pond. Path to discovery. Large Hadron Collider, LHC. The LHC, the world's largest and most powerful particle collider, was constructed by CERN near Geneva, Switzerland, specifically to search for the Higgs boson among other goals. It accelerates protons to near the speed of light and smashes them together, recreating conditions similar to those just after the Big Bang. Experimental evidence. On July 4, 2012, CERN announced that they had found a new particle consistent with the Higgs boson. Two main experiments at the LHC, ATLAS and CMS, both observed a new particle with a mass of about 125 giga-electronvolts, GeV. Scientific and cultural impact. Nobel Prize. In 2013, the Nobel Prize in Physics was awarded to Peter Higgs and Francois Englert for their theoretical discovery of the mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's LHC. Beyond the Standard Model, the discovery of the Higgs boson confirmed the last missing piece of the Standard Model of particle physics. Ongoing research. Further experiments. Research continues at the LHC to study the properties of the Higgs boson in greater detail. Scientists are examining how it interacts with other particles and looking for signs of new physics that might explain dark matter, the imbalance of matter and antimatter in the universe, and other fundamental questions. Upgrades to LHC. The LHC has undergone upgrades to increase its energy and luminosity, allowing more detailed and extensive studies of the Higgs boson and other phenomena. Future projects, like the High Luminosity LHC, HLLHC, aim to produce even more Higgs bosons to study their properties with greater precision. Historical context and development. Early theories and challenges. Before the 1960s, physicists faced a major challenge in explaining how particles acquire mass. The existing theories could not account for why particles like electrons and quarks have mass while others like photons do not. The Higgs mechanism provided a solution to this problem, introducing the concept of the Higgs field, which interacts with particles to give them mass. Higgs breakthrough. In 1964, Peter Higgs, a British physicist, published a paper proposing the existence of a new field that permeates space. Higgs suggested that particles acquire mass through their interaction with this field, and a new particle, the Higgs boson, would be a manifestation of this field. Building the Large Hadron Collider. CERN's role. CERN, the European Organization for Nuclear Research, took on the monumental task of constructing the Large Hadron Collider, LHC, to test these theories. The LHC is a 27-kilometer ring of superconducting magnets housed in a tunnel 100 meters underground, straddling the border between Switzerland and France. Technical feats. Building the LHC involved numerous technical challenges. It required developing new superconducting magnets, advanced particle detectors, and complex data analysis algorithms to handle the enormous amount of data generated by collisions. The discovery. First collisions. The LHC began operations in September 2008, but an electrical fault delayed full operations until November 2009. The first high-energy collisions occurred in March 2010. ATLAS and CMS experiments. The two main experiments searching for the Higgs boson were ATLAS, a toroidal LHC apparatus, and CMS, compact muon solenoid. Both experiments employed vast teams of scientists and massive detectors to observe the products of particle collisions. Impact on physics. Validation of the Standard Model. The discovery of the Higgs boson provided crucial validation for the Standard Model of particle physics, which describes the fundamental particles and their interactions. It confirmed that the Higgs mechanism is responsible for giving mass to elementary particles. New research directions. The Higgs boson's discovery has opened new research directions. Physicists are now studying its properties in detail, looking for deviations from the Standard Model predictions that might hint at new physics. This includes exploring supersymmetry, dark matter candidates, and other theories beyond the Standard Model. Popular culture and public engagement. The God particle, nickname. The term, God particle, popularized by Leon Lederman's book, helped capture public imagination, despite some physicists' objections to the name. It underscored the particle's fundamental role in the universe's structure. Media and outreach. The discovery received widespread media coverage and inspired numerous documentaries, books, and public lectures. It has become a symbol of human curiosity and the quest for knowledge. Future prospects. High luminosity LHC. CERN is upgrading the LHC to the High Luminosity LHC, HLLHC, aiming to increase its luminosity, collision rate, by a factor of 10. This will allow scientists to gather more data and make more precise measurements of the Higgs boson and other particles. New theoretical developments. The discovery of the Higgs boson has spurred new theoretical developments. Physicists are exploring its implications for the stability of the universe, the nature of dark matter, and the possible existence of other Higgs-like particles. Conclusion. The story of the Higgs boson is a tale of theoretical brilliance, technological marvel, and scientific perseverance. From its theoretical inception in the 1960s to its discovery in 2012 and beyond, the journey of the Higgs boson illustrates the collaborative and cumulative nature of scientific progress. It not only answers fundamental questions about the nature of matter but also opens up new mysteries and challenges for physicists to explore.